Continuing on with the sample final, this asks me to find the derivative of number 7 of g of x equals 4 times 5 minus 9x to the 5th. This is a chain rule problem where the inner function of the baby is 5 minus 9x, the outer function of the mommy is to the 5th power times 4. So the first thing we're going to do is take the derivative of the outer function. 5 comes down, 5 times 4 gives me 20. We're going to leave the baby inside of the inner function unchanged, 5 minus 9x. Subtract 1 from the power. So that's the overall derivative of mommy. We now got to worry about derivative of baby. So when I take the derivative of the inside, that 5 goes to 0, and negative 9x becomes negative 9. Cleaning it up a little, negative 9 times 20 gives me negative 180, and I can leave 5 minus 9x to the 4th in parentheses. Question 8 asked me to find dy dx by implicit differentiation. So I need to consider that when I'm multiplying 6x squared times y, this creates a product rule. When I do the product rule, it's first 6x squared times derivative of second, which creates a dy dx, plus second y times derivative of first. 2 comes down and it becomes 12x. Again, I run into a product rule when I see this 8y squared times x. So again, I have to do it as first 8y squared times derivative of second 1 plus second x times derivative of first 16y dy dx. I'm now done with the left side. When I get to the right side, I take the derivative of negative 8. That just equals 0. My goal now is to sort things out into what has a dy dx and what doesn't have a dy dx. So here, this 16xy dy dx and this 6x squared dy dx are going to stay on the same side. It's going to become 6x squared dy dx plus 16xy dy dx. I'm going to move this 12xy and this 8y squared to the other side and make them negative 12xy minus 8y squared. That way, when I factor out this dy dx, I can divide by 6x squared plus 16x. If I divide this side by 6x squared plus 16x, that gives me dy dx, which is what we're looking to isolate whenever we do implicit differentiation. Question 9 asks me to find the absolute extrema of the function on the closed interval. Absolute extrema include two things: endpoints of the interval and any critical values within that interval. The way that I can find what the critical values are is I take the derivative of the function and I set it equal to 0. Here the derivative would be f prime of x equals 3x squared minus, when this squared comes down, 2 times this half goes away, and I'm just left with 3x. If I want to factor 3x squared minus 3x, I can pull a 3x out of both of them, and that's going to leave me with x minus 1. What makes this 0 is x equals 0. What makes this 0 is x equals 1. Both of these are within my interval from negative 5 to 4, so there's 4 total points that I need to test. I'm going to start by finding f of negative 5, then I'm going to find f of 0, f of 1, and finally f of 4. After I put each of these into the original equation, I'm going to see which one's the largest and which one's the smallest. The largest I'll label as the maximum, the smallest I'll label as the minimum. So here, when I do parentheses negative 5 and parentheses to the power of 3 minus parentheses 3 divided by 2 and parentheses negative 5 and parentheses squared, all of that gives me negative 162.5. When I now put in the same equation, except I put in 0 for x, this is going to give me 0 as an answer. I try the same thing again, except now I'm going to put in 1 for x. When I put in 1 for x, it gives me negative 0.5. Finally, I'm going to try 4. When I put in 4 for x, my calculator tells me the answer is 40. Once I've found what the y values are associated with each of these x's, I'm going to identify the lowest y value and the highest y value. Here's my lowest, here's my highest. So my minimum is the lowest. It's occurring at an x value of -5, a y value of -162.5. Here's my max. It's occurring at an x value of +4, a y value of +40.